This is a video for MEI Core Pure Second Order Differential Equations 2, Non-homogeneous equations, 2.6 Particular integrals, special cases. If you've been following this sequence of videos, you will have seen this slide before, and it's just a reminder that in order to solve the non-homogeneous differential equation like this, we first find its complementary function by solving the homogeneous version of the equation. We then find its particular integral by using a trial function related to this right-hand function fx, and then we add those two together, the complementary function and the particular integral, to get the general solution to the equation. We have also seen that these are the types of trial functions we can use depending on the function on the right-hand side, the fx. So for linear functions, we would try a linear function of the form ax plus b. For polynomial functions, we'd try a polynomial of order n. For trig functions that contain either causes of px or sine of px or both, we would use a combination of a cos px plus b sine px. And finally, for exponential functions, we would use a e to the px. So problems can occur if we wish to use a function in the particular integral that's already in the complementary function. So for example, if our complementary function is something like y is equal to a e to the 4x minus b e to the 2x, and our fx on the right hand side of the equation is something like 3e to the 4x, we'd obviously want to use something of this form, and it's already there in the complementary function. And we're going to have a look at an example involving this in a moment. The trick that we use is to multiply through by the independent variable, so instead of using just this on its own, we'll actually add in an extra x. And that enables us to solve the equation and therefore find the particular integral. So let's have a look at this special case then. We've got here that we want to find the general solution of this equation. And here's my right-hand side, the 3e to the 2x. Just to remind us, we've solved this equation a number of times in previous videos. The auxiliary equation is m squared minus m minus 2 equals 0, and that goes through to give me m equals 2 or minus 1. And that gives me a complementary function of this form. Now, here's my problem. That 3e to the 2x is already accounted for in here. And therefore, any type of e to the 2x function that I add in here is really only like changing this arbitrary constant. So the solution is that we try y is equal to ax e to the 2x. So the first derivative, dy by dx, is equal to, it's a product, so we're going to differentiate the first, so a e to the 2x, and then we're going to differentiate the second, so we'll get ax e to the 2x, and we'll get a times 2, so we'll get 2ax e to the 2x. And then if we differentiate a second time, so d2y by dx squared is equal to, this is just an ordinary derivative, so it's just 2a e to the 2x. And this is another product, so we're going to get 2a e to the 2x. And then we're going to get plus, this time it's going to be 4ax e to the 2x. Now if we substitute these bits into the original equation, then I'm going to get 4a e to the 2x plus 4ax e to the 2x. That's from the d2y bit. I'm going to get minus a e to the 2x plus 2ax e to the 2x. And then I'm going to get a minus 2 lots of ax e to the 2x. And that's all got to come out to be 3e to the 2x. So if I look at the things that are just got e to the 2x's in, I'm going to get 4a from this bracket. I'm going to get minus a from this bracket. And I'm going to get nothing from this bracket at the end. And that's equal to 3. So this gives me 3a equals 3, and therefore a equals 1. And so my particular integral is y is equal to x e to the 2x. There's that working written up for you. We know about this as the complementary function, and we can see that e to the 2x, which is over here, is already in the complementary function. So we bring an extra x in the function that we try for the particular integral. There's the derivatives. That's substituted in, and then essentially we've equated the ones that only have e to the x's in. I'm ignoring the terms that have got the x in. So I end up with a equals 1, and hence my particular integral. And so finally, the general solution for this differential equation, there's the complementary function, there's the particular integral. Add them together to give me the general solution. If we have a look at a plot of the solution curve, here's one possible plot with a is 0.5 and b is equal to 2. And notice that we have an intercept here. Well, if we have a look at that, that's when x is equal to 0. And when x is equal to 0, I will get that y is equal to a, e to the 0 is 1, plus b, and of course this bit will be 0. So it's always going to intercept at a plus b. In this case, a plus b is about 1.5, and that looks like it could be okay for this particular curve. So for large x, what happens as x tends to infinity? Well, the big driver in this is going to be this one, because if this is a big number already, this is an even bigger number, so y is going to tend to x e to the 2x, and it will track that blue line here, x e to the 2x, it will track that quite closely. And as x tends to minus infinity, well, this is going to be small, this is going to be small, so this is the only thing that's going to have any significant value, and so y tends to be e to the minus x. Let's have a look at a dynamic plot of that. I've got the red function is my solution, my general solution curve. What happens as we change the parameters? Well, let's watch what happens as we drop the value of a. You can see that the yellow function is going even more steeply, and it's actually dragging the function down, and we get a couple of solutions for y equals 0. If a goes up to 0, then we're just being bounded by these two functions, the 2e to the minus x and the x e to the 2x, and as I alter the value of b for that, you can see it's just lying between those two functions. Now what happens as b goes negative? Well, as b goes negative, all that happens is it's going to flip over, and you'll get the mirror image for the e to the minus x function. So now bend it downwards, and so as x tends to minus infinity, the solution curve goes off towards minus infinity. That was the final video in the sequence second order differential equations 2, non-homogeneous.